Hello and welcome back. So this will be the third video about this this will be the third video about this Kubernetes engine introduction in GCP, and I'm going to start this module, which is Kubernetes architecture here.
Makes it easy to recognize the benefits of innovation initiatives without getting stuck troubleshooting infrastructure issues and managing daily operations. Google Kubernetes engine makes it.
Let's go slower.
Easy to recognize the benefits of innovation initiatives without getting stuck troubleshooting infrastructure issues and managing daily operations related to enterprise scale container deployment. But how does Kubernetes expect you to tell it what to do? And what choices do you have for describing your workloads? The third section of the course was designed to answer those questions. You'll explore Kubernetes concepts like Kubernetes object model and the principle of declarative management, a list of Kubernetes components, Google Kubernetes engine concepts including the autopilot and standard modes of operation, and Kubernetes object management. You'll also get hands-on practice deploying a sample pod in GKE. Let's get started.
Okay, so this module is about instruction to the GKE clusters, and we have also a lab. There are a lot of concepts, 4 videos of concepts, and then the lab. Let's go.
Kubernetes works. It's important to understand 2 related concepts. The first concept is the Kubernetes object model. Each item Kubernetes manages is represented by an object, and you can view and change these objects' attributes and state. The second concept is the principle of declarative management. Kubernetes needs to be told how objects should be managed, and it will work to achieve and maintain that desired state. This is accomplished through a watch loop. A Kubernetes object is defined as a persistent entity that represents a state of something running in a cluster, its desired state, and its current state. Various kinds of objects represent containerized applications, the resources available to them, and the policies that affect their behavior. Kubernetes objects have 2 important elements. The first is an object spec for each object being created. It's here that the desired state of the object is defined by you. The second is the object status, which represents the current state of the object provided by the Kubernetes control plane. By the way, Kubernetes control plane is a term to refer to the various system processes that collaborate to make a Kubernetes cluster work. You'll learn about these processes later. Each object represents a certain type, or kind, as it's referred to in Kubernetes. Pods are the foundational building block of the standard Kubernetes model, and they're the smallest deployable Kubernetes object. Every running container in a Kubernetes system is in a pod. A pod creates the environment where the containers live, and that environment can accommodate 1 or more containers. If there is more than 1 container in a pod, they are tightly coupled and share resources, like networking and storage. Kubernetes assigns each pod a unique IP address, and every container within a pod shares a network namespace, including IP address and network ports. Containers within the same pod can communicate through localhost 127.0.0.1. A pod can also specify a set of storage volumes that will be shared among its containers. Let's explore an example where you want 3 instances of an Nginx web server, each in its own container, to be always kept running. How can this be achieved in Kubernetes? You'll recall that Kubernetes operates off of the principle of declarative management, which means that you'll need to declare some objects to represent those Nginx containers, and in this case, those objects should be pods. From there, it's Kubernetes' job to launch those pods and keep them in existence. Alright, so you've given Kubernetes a desired state that consists of 3 Nginx pods to be always kept running. We did this by telling Kubernetes to create and maintain 1 or more objects that represent them. Now Kubernetes will compare the desired state to the current state. For this example, let's say our declaration of 3 Nginx containers is completely new, meaning the current state does not match the desired state. So Kubernetes, specifically its control plane, will remedy the situation. Because the number of desired pods running for the object you declared is 3, and 0 are presently running, 3 will be launched. And the Kubernetes control plane will continuously monitor the state of the cluster, endlessly comparing reality to what has been declared, and remedying the states as needed.
Okay. Now, next activity. We have other 3 videos.
The Kubernetes control plane is the fleet of cooperating processes that make a Kubernetes cluster work. Although you might only directly work with a few of these components, it's important to understand what the fleet does and the role they each play. In this section of the course, you'll get an opportunity to see how a Kubernetes cluster is constructed, part by part. This will help illustrate how a Kubernetes cluster that runs in GKE is easier to manage than one you provisioned yourself. First, a cluster needs computers, and these computers are usually virtual machines. They always are in GKE, but they could be physical computers too. One computer is called the control plane, and the others are called nodes. The node's job is to run pods, and the control planes is to coordinate the entire cluster. Let's look at the control plane components. Several critical Kubernetes components run on the control plane. First is the Kube API server component, which is the only single component that you'll interact with directly. The job of this component is to accept commands that view or change the state of the cluster. This includes launching pods. Next is the kubectl command. The job of the kubectl command is to connect to the Kube API server and communicate with it using the Kubernetes API. The Kube API server also authenticates incoming requests, determines whether they are authorized and valid, and manages admission control. But it's not just kubectl that talks with Kube API server. In fact, any query or change to the cluster state must be addressed to the Kube API server. There is the etcd component, which is the cluster's database. Its job is to reliably store the state of the cluster. This includes all the cluster configuration data, along with more dynamic information, such as what nodes are part of the cluster, what pods should be running, and where they should be running. You'll never directly interact with etcd. Instead, the Kube API server interacts with the database on behalf of the rest of the system. Next is kubescheduler, which is responsible for scheduling pods onto the nodes. Kubescheduler evaluates the requirements of each individual pod and selects which node is most suitable. However, it doesn't do the work of actually launching pods on nodes. That's done by another component. Instead, whenever it discovers a pod object that doesn't yet have an assigned node, it chooses a node and writes the name of that node into the pod object. How does kubescheduler decide where to run a pod? It knows the state of all the nodes, and also obeys constraints you define regarding where a pod can run, considering hardware, software, and policy details. For example, you might specify that a certain pod is only allowed to run on nodes with a specific amount of memory. You can also define affinity parameters, which specify when groups of pods should run on the same node. Alternatively, you can define anti-affinity parameters, which ensure that pods do not run on the same node. The Kube Controller Manager component has a broader job. It continuously monitors the state of a cluster through the Kube API server. Whenever the current state of the cluster doesn't match the desired state, Kube Controller Manager will attempt to make changes to achieve the desired state. It's called the Controller Manager because many Kubernetes objects are maintained by loops of code called controllers, which handle the process of remediation. You can use certain Kubernetes controllers to manage workloads. For example, remember our problem of keeping 3 Nginx pods always running? They can be gathered into a controller object called a deployment that runs, scales, and brings them together underneath the front end. Other types of controllers have system-level responsibilities. For example, the node controller's job is to monitor and respond when a node is offline. The Kube Cloud Manager component manages controllers that interact with underlying cloud providers. For example, if you manually launched a Kubernetes cluster on Compute Engine, Kube Cloud Manager would be responsible for bringing in Google Cloud features like load balancers and storage volumes. Now let's shift our focus to nodes. Each node runs a small family of control plane components called a kubelet. You can think of a kubelet as Kubernetes agent on each node. When the Kube API server wants to start a pod on a node, it connects to that node's kubelet. Kubelet uses the container runtime to start the pod and monitors its lifecycle, including readiness and liveness probes, and reports back to the Kube API server. The term container runtime, which was mentioned earlier in this course, is the software used to launch a container from a container image. Kubernetes offers several container runtime choices, but the Linux distribution that GKE uses for its nodes launches containers that use Containerd, the runtime component of Docker. And finally, there's the Kube proxy component, which maintains network connectivity among the pods in a cluster. In open source Kubernetes, network connectivity is accomplished by using the firewalling capabilities of IP tables, which are built into the Linux kernel. We saw that the Kubernetes control plane is a complex management system, but how is GKE different from Kubernetes? From the user's perspective, it's a lot simpler. GKE manages all the control plane components for us. It still exposes an IP address to which we send all of our Kubernetes API requests, but GKE is responsible for provisioning and managing all the control plane infrastructure behind it. It also eliminates the need for a separate control plane. Node configuration and management depends on the type of GKE mode you use. With the autopilot mode, which is recommended, GKE manages the underlying infrastructure such as node configuration, auto-scaling, auto-upgrades, baseline security configurations, and baseline networking configuration. With the standard mode, you manage the underlying infrastructure, including configuring the individual nodes.
Okay, so nice. A lot of new informations for me.
Now let's explore the 2 available modes of operation, autopilot and standard mode, in more detail. At a high level, autopilot mode optimizes the management of Kubernetes with a hands-off experience. However, less management overhead means less configuration options. And with autopilot GKE, you only pay for what you use. The standard mode allows the Kubernetes management infrastructure to be configured in many different ways. This requires more management overhead, but produces an environment for fine-grained control. With GKE standard, you pay for all of the provisioned infrastructure, regardless of how much gets used. Let's examine the benefits and functionality of autopilot in more detail. Autopilot is optimized for production. As a Google-managed and optimized GKE instance, the job of autopilot is to create clusters according to battle-tested and hardened best practices. Autopilot defines the underlying machine type for your cluster based on workloads, which optimizes both usage and cost for the cluster and adapts to changing workloads. And without the cluster management overhead, autopilot lets you deploy production-ready GKE clusters faster. Autopilot also helps produce a strong security posture. Google helps secure the cluster nodes and infrastructure, and it eliminates infrastructure security management tasks. By locking down nodes, Autopilot reduces the cluster's attack surface and ongoing configuration mistakes. Autopilot promotes operational efficiency. Google monitors the entire Autopilot cluster, including control plane, worker nodes, and core Kubernetes system components. This way, it ensures that pods are always scheduled. This level of monitoring allows Google to always keep clusters up to date. Autopilot also provides a way to configure update windows for clusters to ensure minimal disruption to workloads. With Autopilot, Google is fully responsible for optimizing resource consumption. This means you only pay for pods, not nodes. Now that you've seen many of the Autopilot mode benefits, let's look at some restrictions presented with this operation mode. The configuration options in GKE Autopilot are more restrictive than in GKE Standard. This is because GKE Autopilot is a fully managed service and has a pod scheduling service level agreement. Autopilot clusters also have restrictions on access to node objects. Features like SSH and privilege escalation were removed, and there are limitations on node affinity and host access. However, all pods in GKE Autopilot are scheduled with a guaranteed class quality of service, or QoS, but this requires a minor configuration change. The GKE Standard mode has the same functionality as Autopilot, but you're responsible for the configuration, management, and optimization of the cluster. Unless you require the specific level of configuration control offered by GKE Standard, it's recommended that you use Autopilot mode. Let's finish up this section of the course by exploring Kubernetes object management. It's important to know that all Kubernetes objects are identified by a unique name and a unique identifier. Recall the earlier example where you wanted the 3 Nginx web servers to run all the time. The simplest way to achieve this is by declaring 3 pod objects and specifying their state. For each, a pod must be created and an Nginx container image must be used. Let's see how to make this declaration. You define the objects you want Kubernetes to create and maintain with manifest files. These are ordinary text files that can be written in YAML or JSON. You'll see YAML used in this course. This manifest file defines a desired state for a pod, its name and a specific container image for it to run. Required fields include API version, which states the Kubernetes API version used to create the object, kind, which states the object you want, in this case a pod, and metadata, which identifies the object name, unique ID, and an optional namespace. If several objects are related, it's a best practice to define them all in the same YAML file. This makes things easier to manage. We strongly recommend saving YAML files in version control repositories, so it's easier to track and manage changes and undo those changes. If are related, it's a best practice to define them all in the same YAML file. This makes things easier to manage. We strongly recommend saving YAML files in version control repositories, so it's easier to track and manage changes and undo those changes when necessary. It's also helpful when recreating or restoring a cluster. Cloud source repositories is a popular service for this purpose. Let's look at the details of an object. First, all objects are identified by a name. Names must consist of a unique string under 253 characters. Numbers, letters, hyphens, and periods are allowed. Only one object can have a particular name at the same time in the same Kubernetes namespace. After an object is deleted, however, the name can be reused. Second, every object created throughout the life of a cluster has a unique identifier, or UID, generated by Kubernetes. And third, there are labels. Labels are key value pairs to tag objects during or after their creation. Labels help identify and organize objects. A way to select Kubernetes resources by label is through the kubectl command. For example, this command can select all the pods that contain a label called app with a value of Nginx. Label selectors can be used to ask for all the resources that have a certain value for a label, all those that don't have a certain value, or even all those with a value in a set you supply. Now, let's go back to our example. One way to create 3 Nginx web servers is by declaring 3 pod objects, each with its own section of YAML. In Kubernetes, a workload is spread evenly across available nodes by default. So how do you tell Kubernetes to maintain the desired state of 3 Nginx containers? To maintain an application's high availability, you need a better way to manage it in Kubernetes than specifying individual pods. One option is to declare a controller object. A controller object's job is to manage the state of the pods. Because pods are designed to be ephemeral and disposable, they don't heal or repair themselves, and they're not meant to run forever. Examples include deployments, stateful sets, daemon sets, and jobs. Deployments are a great choice for long-lived software components like web servers, especially when you want to manage them themselves, but they're not meant to run forever. Examples, one option is to declare a controller object. A controller object's job is to manage the state of the pods. Because pods are designed to be ephemeral and disposable, they don't heal or repair themselves, and they're not meant to run forever. Examples include deployments, stateful sets, daemon sets, and jobs. Deployments are a great choice for long-lived software components like web servers, especially when you want to manage them as a group. In our example, the practical effects of the deployment controller is to monitor and maintain the 3 Nginx pods. When the kube scheduler schedules pods for a deployment, it notifies the kube API server. The deployment controller creates a child object, a replica set, to launch the desired pods. If one of these pods fails, the replica set controller will recognize the difference between the current state and the desired state, and will try to fix it by launching a new pod. So, this means that instead of using multiple YAML manifests or files for each pod, you used a single deployment YAML to launch 3 replicas of the same container. Within a deployment object spec, the number of replica pods, which containers should run the pods, and which volumes should be mounted, the following elements are defined. Based on these templates, controllers maintain the pod's desired state within a cluster. It's time for some hands-on practice with GKE. In the lab titled Deploying GKE Autopilot Clusters, you'll build and use GKE clusters, then you'll deploy a sample pod. Specifically, you'll use the Google Cloud Console to build GKE clusters, deploy a pod, and then examine the cluster and pods.
Okay, this will be a quick lab. Let's see. Yeah, it's just 2 tasks, 3 tasks. Okay, so we already clicked start. Let's see. Okay. Next. Let's go. Okay, so task 1, deploy JKE clusters. We go to JKE, create a JKE cluster exam. You can autopilot cluster 1. So JKE clusters, create. Let's get started. Okay, so the name is already the same, and US West 1. Okay, click create. Now we need to wait a little. Let's see. Oh, it's already running. No? Oh. %29%. Okay, so this will take maybe, oh, but you're not able to see what I was doing here. Okay, so now you can see here that I created a cluster, and it's 54% on its way. Okay. We're nearly done. So now it's deploying. Then we will create a deployment. So the deployment will be named like this. Okay. Oh shit! I was destroying all my lab here. Oh, 67%. Okay, then after there's another module with a quick lab. So let's go. I can finish this course today. Okay, so mode autopilot. Public endpoint. So it has one pod. It's curious that this percentage here corresponds to the number of tasks performed, but not to the time needed to perform the tasks. That's a curious dissonance. Whatever. So while here, let's see if we can check something about the new exam. Yeah, which is GCP Cloud Architect certification. Okay, so the exam guide did not change. Then this is the advised course, which we already are doing. Yeah, okay. Oh wow, this is new for me. Join the no-cost innovators community and receive 35 monthly credits to use on courses and labs and skill. Okay. We had our full catalog of training and labs, unleash the power of Google Developer Premium annual subscription. Secures photo. Okay, so let's see. Okay, now we have the cluster ready here, so I will stop my random wandering. Okay, we have the cluster ready. And here we have the storage classes, all the storage used by our cluster. We copy these and go to create a deployment. Deploy. Oh, it's from another, it's from workloads. Create a deployment. Enter nginx latest and deploy. Let's see. Okay. Okay, so this I think will be kind of faster. So while this is happening, let me have a watch at certification GCP Cloud Architect. Yeah, let's go here. Train, review, view, partner, join. Let me see about this. Start training. So in Web Assessor, you have to register here. Okay. Okay, so guide to preparing blah blah to architect certification. Oh man, this is kind of obsolete. Let's see. Y become, yeah. Okay, so it's 2 hours registration fee. Language is English or Japanese. 60, 60, 50, 60 multiple choices. 1 proctored exam from a remote location or take on site proctored exam testing center. So yeah, I will find one which is better for me. Okay, so let's see. Now we have the deployment with some errors apparently. Yeah, let's see. It says okay, even if we have these errors. It says okay anyway. Oh, okay, so it was just a temporary state temporary information. Now let's see what they advise here. Go to workloads, to ngx. Click details tab for ngx workload. The details tab show more details about the workload, including the pod specification, number of status of pods. Okay. Click the revision history tab. Click the event tab. Okay, and here we have the logs. Okay, and then the YAML. Sorry, I got some flu. Okay, so click the overview tab. Managed pods. The pod detail page provides information pod configuration. The pod details page you can events logs, details to container logs in cloud operation. Okay, I click on to be YAML file. Okay, so here for each of the pod you can see all these details. Nice, let's end everything. Let's go. Next. Now we have a quick quiz. When designing an application, you want the containers to be located as close to each other as possible in order to minimize latency. Which design decision helps meet this requirement? As possible. Well, this may be in the same pod. GKE offers two modes of operation, autopilot and standard. Which one of the options below is a use case for using standard mode? You require SSH access to the node. That may be. Machine types based on workloads. That's already available in autopilot. You want to only pay for pods and not nodes. That's possible only in autopilot. You want to avoid cluster configuration. Okay, so this is the answer. You want to deploy multiple copies of an application in an effort to load balance traffic. How should you deploy pods to production to achieve this? Create a service manifest for the load balancer that specifies the number of replicas you want to run. Create a deployment manifest that specifies the number of replicas that you want to run. Deploy the pod manifest. Yeah, okay. Next. So now in this same video we'll start this new module which is called Kubernetes operations, which is really short. Therefore, let's go.
Command line tool to interact with GKE clusters. Because it allows you to manage Kubernetes resources from the command line, it makes it easy to automate tasks and to troubleshoot problems. But how does it work? Does it need special configuration? How can it be used to gather information about the containers, pods, services, and other engines running within the cluster? The goal of this final section of the course, titled Kubernetes Operations, was designed to answer those questions. You'll explore kubectl and how to configure it, and what introspection means and how it can be used to troubleshoot a cluster. You'll also get hands-on practice deploying Google Kubernetes Engine clusters from Cloud Shell. Okay, let's get started. So what exactly is the kubectl command, and why is it important? kubectl is a utility used by administrators to control Kubernetes clusters. It's used to communicate with the kube API server on the control plane. This is important to users because it allows them to make requests to the cluster, and kubectl determines which part of the control plane to communicate with. Within a selected Kubernetes cluster, kubectl transforms command line entries into API calls and sends them to the kube API server. However, to work properly, kubectl must be configured with the location and credentials of a Kubernetes cluster. And before kubectl can be used to configure a cluster, it must first be configured. kubectl stores its configuration in a file in the home directory in a hidden folder named .kube and contains a list of clusters and the credentials that will be attached to each of those clusters. But where do the credentials come from? GKE provides them through the gcloud command. To view the configuration, either open the config file or use the kubectl command config-view. Please note that the kubectl config shows the configuration of the kubectl command itself, whereas other kubectl commands show the configurations of cluster and workloads. For example, let's say an administrator wants to see a list of pods in a cluster. After connecting kubectl to the cluster with proper credentials, the administrator can issue the kubectl getPod command. kubectl then converts this command into an API call, which it sends to the kube API server through HTTPS on the cluster's control plane server. From there, the kube API server processes the request by querying etcd. The kube API server then returns the results to kubectl through HTTPS. Finally, kubectl interprets the API response and displays the results to the administrator at the command prompt. To connect kubectl to a GKE cluster, first retrieve the credentials for the specified cluster. This can be done with the getCredentials gcloud command in any other environment where the gcloud command line tool and kubectl are installed. Note that both are installed by default in Cloud Shell. By default, the gcloud getCredentials command writes configuration information into a config file in the .kube directory in the home directory. If this command is rerun for a different cluster, it will update the config file with the credentials for the new cluster. This configuration process only needs to be performed once per cluster in Cloud Shell, because the .kube directory and its contents stay in the home directory. The gcloud command is how authorized users interact with Google Cloud from the command line. If authorized, the gcloud getCredentials command provides the credentials needed to connect to the GKE cluster. Although kubectl is a tool for administering the internal state of an existing cluster, it can't create new clusters or change the shape of existing clusters. That's done through the GKE control plane, which the gcloud command and the Google Cloud Console interfaces to. After the config file in the .kube folder is configured, the kubectl command automatically references this file and connects to the default cluster without prompting for credentials. Now let's explore how to use the kubectl command. kubectl's syntax is composed of 4 parts: the command, the type, the name, and optional flags. The command specifies the action that you want to perform, such as get, describe, logs, or exec. Some commands show information, whereas others change the cluster's configuration. The type defines the Kubernetes object that the command acts upon, like pods, deployments, nodes, or other objects, including the cluster itself. The type used in combination with command tells kubectl what you want to do and the type of object you want to perform that action on. The name specifies the object defined in type. The name field isn't always needed, especially when using commands that list or show information. For example, if you run the command kubectl getPods without specifying a name, the command returns the list of all pods. To filter this list, specify a pod's name, such as kubectl getPod myTestApp, and kubectl will return only information on the pod named myTestApp. Some commands let you append flags to the end, which you can think of as a way to make a special request. For example, to view the state of a pod, use the command kubectl getPod myTestApp-o equals YAML. Also, it's worth mentioning that telling kubectl to produce a YAML output can be helpful for other tasks related to Kubernetes objects, for example, recreating an object in another cluster. Flags can also be used to display additional information. For example, run the command kubectl getPods-o equals wide to display the list of pods in wide format, which reveals pods in the list. Wide format also displays which node each pod is running on. The kubectl command has many uses, from creating Kubernetes objects to viewing them, deleting them, and viewing or exporting configuration files. Now that you've been introduced to the kubectl command, which is the way to specify the action that you want to perform on a Kubernetes cluster, let's explore how to debug problems when an application is running. This process is called introspection. It's the act of gathering information about the containers, pods, services, and other engines that run within the cluster. We'll start with 4 commands to use to gather information about your app: get, describe, exec, and logs. A good place to start is with pods, the basic units of Kubernetes. A simple kubectl getPods command tells you whether your pod is running. It shows the pod's phase status as pending, running, succeeded, failed, or unknown, or crash loop back off. The phase provides a high-level summary, not the comprehensive details about a pod or its containers. The pending status indicates that Kubernetes has accepted a pod, but it's still being scheduled. This means that the container images defined for the pod have not yet been created by the container runtime. For example, when images are being pulled from the repository, the pod will be in the pending phase. A pod runs after it is successfully attached to a node, and all its containers are created. Containers inside a pod can be starting, restarting, or running continuously. Succeeded means that all containers finish running successfully, or instead, that they terminated successfully and they won't be restarted. Failed means a container terminated with a failure and it won't be restarting. Unknown is where the state of the pod simply cannot be retrieved, probably because of a communication error between the control plane and a kubelet. And crash loop backoff means that one of the containers in the pod exited unexpectedly, even after it was restarted at least once. This is a common error. Usually this means that the pod isn't configured correctly. To investigate a pod in detail, use the kubectl describe pod command. This command provides information about a pod and its containers, such as labels, resource requirements, and volumes. It also details the status information about the pod and container. For pods, the name, namespace, node name, labels, status, and IP address are displayed. For containers, the state, waiting, running, or terminated, images, ports, commands, and restart counts are displayed. Single command execution using the exec command lets you run a single command inside a container and view the results in your own command shell. This is useful when a single command, such as a ping, will do. And finally, the logs command provides a way to see what is happening inside a pod. This is useful in troubleshooting. And finally, ports in your own. Single command execution using the exec command lets you run a single command inside a container and view the results in your own command shell. This is useful when a single command, such as a ping, will do. And finally, the own command shell. This is useful when a single command, such as you run a single command inside a container and view the results in your own command shell. This is useful when a single command, such as a ping, will do. And finally, the logs command provides a way to see what is happening inside a pod. This is useful in troubleshooting, as the logs command can reveal errors or debugging messages written by the applications that run inside pods. The logs contain both the standard output and standard error messages that the applications within the container have generated. The logs command is useful to output and find out more information about containers that are failing to run successfully. And if the pod has multiple containers, you can use the -c argument to show the logs for a specific container inside the pod. Let's do a scenario where you need to work inside a pod, maybe to run a command. Let's say you need to install a package, like a network monitoring tool or a text editor, before you can begin troubleshooting. To do so, you can launch an interactive shell using the -it switch, which connects your shell to the container that allows you to work inside the container. This syntax attaches the standard input and standard output of the container to your terminal window or command shell. The -i argument tells kubectl to pass the terminal standard input to the container, and the -t argument tells kubectl that the input is a TTY. If you don't use these arguments, then the exec command will be executed in the remote container and return immediately to your local shell. Now, it's important to note that it's not a best practice to install software directly into a container, as changes made by containers to their file systems are usually ephemeral. Instead, consider building container images that have exactly the software you need, instead of temporarily repairing them at runtime. The interactive shell will allow you to figure out what needs to be changed to solve a problem, but you should then integrate those changes into your container images and redeploy them.
Okay, makes sense. Wait. Okay, now we have a lab.
It's time for the last hands-on lab of this course. In the lab titled Deploying GKE Autopilot Clusters from Cloud Shell, you'll use the command line to build GKE clusters. You'll inspect the kubeconfig file and use kubectl to manipulate the cluster.
Okay, let's go. In this task, you use Cloud Shell to deploy GKE clusters. So first of all, we create these environment variables. Okay. Now, Cloud Shell type the follow command to create a Kubernetes cluster if prompted clearly authorize. Okay. So gcloud container clusters create auto my cluster autopilot cluster 1 in US West 1. Authorize. This form of the command sets most options to their defaults. So The entire set of possible options refer to Google Cloud Containers or create reference. Jesus. You will see a number of warnings highlighting blah blah blah. You need to wait a few minutes for the cluster deployment to complete. Yeah, it's like it will take, it's 5 minutes, I think. Connect to a GKE cluster. Okay. So while in this terminal we're waiting for the cluster creation, here we launch this. Wait, so we create the variables also in this terminal. So now we can launch this. This command creates a .cube directory in your home directory if it doesn't already exist. In the cube directory, the command creates a file named config if it doesn't already exist, which is used to store the authentication configuration information. The config file is typically called kube config file. Where am I? Oh, jeez. I'm in home. What the fuck? Ls show hidden directories. So it's not, it hasn't been created, I think, as the cluster is not running yet. Therefore, I will need to wait for the cluster to be launched. I will just have a little pause meanwhile. Okay, while waiting this to complete, focus again the camera, and let's go to search cloud certification GCP book exam. Okay. So I'm not sure if I have an account here. I should have it. Well, then what happens? Mm-hmm. Okay, so this is quite simple. You just pay and then you receive a code. Okay, now the cluster is running and we should be able to get credentials now. Okay, therefore now we should have this available. ls, let's see. Oh, sorry. So pound. Okay, ls cd up. ls. What the fuck? What is this? I mean, ls minus all and ls minus ap. Can't see this. ls minus a and I cannot see this cube directory in my. Sorry, I need to understand this. Oh, so it's here. It's not. I mean, it's in the user's home. Ah, fuck this shit. So now we'll do the nano config thing. Okay, API version 1, cluster certificate authority data server name JKE. Okay, context user context current context. You can now examine. Okay, Ctrl X to exit. Okay. Yeah, to print out the content of the kubeconfig file. Okay. What does source in Linux do? Wow. To the play Nginx, put name in Nginx one. Oh, maybe because the get pods. Yeah, the pod is still not running. It's pending. Okay, now it's running. And we continue with top node. Now we receive, fuck. Let's say rerun the above command. You know what, I don't care. Shows you information across the deployed pods in the cluster. So we can just copy the name of this pod and paste it here. Okay. Describe pod. Okay, it has a lot of information. Push a file into a container. Nano test HTML. This is title. Hello world. Now we copy. Enclose shall execute the following command to place the file into the appropriate location within the Nginx container in the Nginx pod to be served statically. So copy. Okay, so it's a copy command inside kubectl. This command copies blah blah blah, expose the pod for testing. So kubectl expose pod. Enclose shall get cluster get services. Okay, shall sample again, next step, output. What? Okay, now check my progress. Now we can download. Jesus Christ. The external IP is this one. This is title hello world, okay. Okay. You connect to a pod to adjust settings, edit file, okay. Prepare the environment, so git clone. Create a soft link as a shortcut to the working directory. We're nearly done. Okay, we create the soft link. Jesus, man. Oh, man, come on. What the fuck? AK8S. Jesus fucking Christ. What the fuck is that red? This is an archive. I think. Oh, let's see. Where the fuck am I? Ah, that's a soft link. Okay. But wait a second. Shouldn't I have? Sorry, but where is this going? In case one does not specify anything. I mean, I'm missing the files here. Oh, whatever. I will just repeat. have it. Now this should work. Okay. So we already have a YAML file to deploy a pod, which will have a container called new ngx. And we just have to use kubectl apply -f that YAML. Okay. Okay, so get pods. It needs something like a minute, if I'm not wrong. My god, this is a long task. Fucking long task. Okay, nice. Now we create a connection. So from here we are acting as root inside the container. Now we can execute an update, and we can install Nano. Yes. Create a new file. We modify it. Yes. We exit from this modality, which we accessed with kubectl exec it to connect and test the modified engine connector. Kubeport. Okay, now I can download the file. Perfect. Now in a third Cloud Shell session, we get the logs. Okay, so we run this command and we get, okay, this Review the additional log messages, close the third, close the original. Okay. We can leave everything and end the lab. Oh shit. Oh my god. Now we go for the quiz and we finish this course finally. You want to use kubectl to configure your cluster, but first you must configure it. Where does the kubectl command store its configuration file? The configuration information is stored in environment variables in the current shell. The configuration information is stored in the home kube config file. You attempt to update a container image to a new version by using the kube describe pod command, but are not successful. The output of the command shows that the pod status has changed to pending. The state is shown as waiting, and the reason is shown is image pulled back off. What is the most probable cause of this error? What command can be used to identify which containers in a pod are successfully running and which are failing or having issues? Which command can be used to display error messages from containers in a pod that are failing to run successfully? Nice. So maybe it's exec or describe pod, not sure. Yeah, however, let's continue and finish.
This brings us to the end of the Getting Started with Google Kubernetes Engine course. Let's do a quick recap. In the first section of the course, you explored the definition of cloud computing.
Okay, we got another badge. I'm very satisfied, and we finished this course.
Welcome to the two-part course on logging, monitoring, and observability in Google Cloud. The core operations tools in Google.
No, please. So, just to have a quick overview of my learning path, we just finished this course here, and in the next videos I will start dedicating time to this course, logging and monitoring Google Cloud. Therefore, thank you for being here with me. I hope you enjoyed this video. See you in the next one. Bye.